Welcome back to Code Insights. So in this new video we are going to talk about a special topic, counting sort. So welcome back, and let's see how the counting sort works and what is this counting sort, and let's get to know how to do this counting sort. So let's begin. So first, let's see what is this counting sort. So as we know many sorting algorithms. Most of them are comparison sorts. So as an example, we can say bubble sort, selection sort, merge sort, quick sort. So these all are comparison sorts. So we are going to compare the value and then swap or not. So this counting sort is not a comparison sort. So what is this? So in this comparison sort, we are going to sort the values according to the keys. The given key values, you can say the same time this sorting algorithm is, as the name, you are going to count the number of elements which having distinct key values. That means different key values. So what is this key value and how we are going to count, how we are going to sort, let's see in this video. Now let's see when counting sort is used, the use cases and some constraints. So first let's see when the counting sort can be used. So the counting sort is used when the input data consists of integers, the range of values are small, the minimum value is known and can be found, and stable sorting is required. So as real world examples, we can say sorting students marks from 1 to 100, or the sorting ranks from 1 to 5, like that. So talking about the constraints, that means when not to use the counting sort. The counting sort should not be used when the range of values is very large and the input contains decimal or floating point numbers and memory usage is limited, because counting sorts use extra memory. It is not efficient for large ranges. So what is the key idea behind this algorithm? The key idea of counting sort is very simple. So instead of sorting by comparison, we count how many times each number appears and use that count to determine the exact position of each element in the sorted array. So the algorithm answers the question how many elements are smaller than or equal to this value. So before we are going to start the sorting, we must know some assumptions about input range. So counting sort assumes input contains non-negative integers and minimum value is usually 0 and maximum value is known or can be calculated. So if the maximum value is k, then the size of the counting array will be k plus 1. So let's see how this counting sort works step by step. So the first step is finding the maximum value. So with our input array, the first step is for us to find the large value in our input array. So as you can see from these given values, the largest value is 7. So this is a common linear time operation, and most programming languages provide helper methods to make this work with little effort. So the step 2 is creating a count of all values. So next we want to create a running count of how often each value in our input occurs. So in looking at our numbers, we can see that 0 appears twice, 1 appears twice, 2 appears twice, like that, so on. So we want to calculate this in a more scalable way. What we can do this is by first creating a new array called count, whose keys represent each unique value from our input array. So what I just said sounds complicated, but let's break down this and simplify it. The maximum value in our input array is 7. This means that in our count array, the highest key will have a value of 7 as well. So what exactly does this mean? This means something like this. So as you can see in here, in the count array. So in the world of arrays, the key is the index position. When the largest value in our input array is 7, and we know that array index positions always start with 0. All of our input values will be represented somewhere between 0 and 7. So our main work is to create an array whose size is 1 greater than the maximum value to allow for an index position of 7 to exist. So in here, as you can see, what we now have is a count array made up of 8 empty items. The item position of this array maps to values that could exist in our input array for the index position starting from 0 and go all the way to the maximum value of 7. So from here, it is a counting exercise. When we encounter each value from our input array, we go to the corresponding entry in our count array and increment the value by 1. At the end of this, our count array will look as the here in this, like this. So each index position corresponds to a value in our input array, and each value at the index position is nothing more than a count of the number of times this index position appeared as a value in input. So like this. So by looking at the final state of our count array, there is something else we can observe. We can sort or reconstruct what a sorted version of our input array will look like. But this is an illusion, it's not what we want. So if you are curious as to why, we can call it down like this. So are we done sorting our input array? So with this information about the count of each value, believe it or not, we have what it takes to construct our sorting array, kind of. So our count array index positions all already go from 0 to 7 in a perfect increasing order and capture the full range of values from our input. So we can also see that 0 appears twice, 1 appears once, 2 appears twice, 3 appears once, 4 appears twice, 5 appears once, 6 doesn't appear at all, and 7 appears just once. So all we need to do is build up our sorted output array with this information, like this. So there is a big catch here. So if all we are ever going to sort our integer values with no regard for stability, then yes, we are done. For real world scenarios, that's too limiting. So what we will typically sort will include more than just integer values. So we have also seen the stability, the property where the initial order of similar items is preserved in the final order is also important. So now we are not done. So the next step will be calculating the final position. So if we take stock of what we have right now, we have our count array and our input array. Our input array is just sitting there with its unsorted values happily loitering. The count array stores a count of number of each item's distinctive element from the input array appears. So each distinctive element is represented as the index position in our count array. So what we are going to do next is evaluate our count array to better describe the sorted position each item will ultimately be in. So in the earlier note, we visually look at the arrangement of each item and where it will land. So let's go ahead and formalize it by storing the cumulative sum or the prefix sum at each array position instead of the count value. So this will involve us taking each array item starting at index position 1, or we can say the second item, and adding its value with the value in the previous array item. So like this, in the in this given image you can see that process. So but we count value now show is no longer the count. Instead they show where each corresponding value from the input array as specified by the count array's index position will need to appear in the sorted output array. So if we translate each value into index positions, it will look like this. So because index positions start at 0 and our cumulative sum value start at 1, the numbers are offset by 1 when we look at the output array to determine the final index positions of our sorted values. So the next step is placing the elements in order. So we are now in our final step. Here we will take our unsorted elements from our input array, map them with the locations we calculated in our count array, like in the previous step, and fill our output array with the correct values in their sorted location. So this is relatively easy, but it is tedious with a handful of steps. So we'll walk through the steps together very slowly, and this is our currently starting point. So you can see the input array, count array, and the output array. So our input array will be primary driver of all the remaining steps we are about to see, and we will be iterating through all the values in our input array in reverse. There is a reason for that, and we'll talk about that a bit later. So let's see at the end where we have our second value 2. So as you can see, so we use this 2 value as the key or the index position in an array to find the corresponding value in our count array. So like this, the value at the position indicated by 2 value is 6. This 6 defines the position our last item in the input array. The one with the 2 value will be when sorted. Because the 6th position needs to account for 0 based indexing, we reduced it by 1 and to find the index position 5 in our output array. This. So now what we have found that we have found the sorted position our 2 value will be in, we can go ahead and place it in our output array like there. So we found our exact position for number 2. So there is one more step remaining in our count array. We will decrement by 1 the sorted value at the index position 2 to indicate that we have already used it. In our case, the sorted value of 6 will now become a 5. Like this. So this is to ensure that any future attempts to find out where to place a value of 2 will not create a collision and overwrite a previously sorted value. So when we encounter a 2 in our input array again, this time we will see that its sorted position is at 5. So we will place it at index position 4 instead. So we'll get to this shortly when we encounter our adjacent 0 values in the input array. So we don't need to talk about this detail just yet. So what we saw was a very slow and detailed look at how we figure out how to place an unsorted item in the correct sorted position. So we are going to speed things up a little bit and repeat these similar steps. So now we go down our input array to the next item, which has a value of 7. We know that 7 has count value of 11, and this means its index position in our output array will be 1 less than that, which is 10. So we also decrement the value of 11 in our count array to 10 to account for any future instances of 7, if any, finding a location. So go down our input array. Our next value is 4. So this 4 value maps to position 9 in our count array, and this means that 4 goes into index position 8. That means 9 minus 1 in our output array, and as our last sub step we decrement the value of 9 to 8 in our count array. Next up we have value 0, 0, and the step we saw earlier repeats. So moving along, we have another 0 value in the second here, and when we repeat the step, the state of our 3 arrays will be as follows. So because this is the second time the 0 value is being placed, we can see the importance of decrementing the position value in our count array after we place our item. When we encountered 0 for the first time a few steps ago, the corresponding value was 2. So after placing the first 0, we decrement the value to 1. So this ensured when we encountered 0 again in this step, because the corresponding value was now 1, we were able to place it at index position 0 in our output array and not have to deal with the collision. So at this point you should have a good understanding of how each subsequent item from our input array will go through the count array and then be properly placed in the output array. So at the end of all these steps, the final state of our 3 arrays will be as like this. So of course the only detail we really care about is what the output array shows, and what we see there is a properly sorted array. Now let's talk about the stability of counting sort. A sort algorithm is called stable if equal elements keep their original order. So counting sort is stable because we process the input array from right to left, and duplicate elements maintain their relative order. So because of this, counting sort is often used in radix sort. And to conclude this video, I would like to talk about some advantages and limitations of counting sort. So as advantages, we can say it's very fast for small ranges and linear time complexity and stable sorting algorithm and no element comparisons, and uses simple logic. So as limitations, this is not suitable for large ranges and requires extra memory and works only for integers, and not an in-place sorting algorithm. So with this, I would like to conclude this video about counting sort, and thank you for joining with me in this video. So let's meet in this next video. Bye.